Hey guys, and welcome back to Quantic Academy. So today we're doing centripetal motion. Okay, so circular motion is what it is. You just move in a circle. And so your velocity will be here at some point, it'll be here, it'll be here. And as you can see, the velocity is changing. Now if velocity is changing, then that means there must be an acceleration. Okay? Now, if you do the math, it's complicated math. It's beyond the scope of the video. If you want me to make a video explaining where centripetal force and acceleration, how to derive it, and stuff like that, then let me know in the comments. So if you do the math, you figure out that the centripetal acceleration points towards the center of the circle. Always. It always points towards the center of the circle, no matter where you are on the circle. Okay? So the centripetal acceleration, its magnitude is given by v squared over r. And the centripetal force is just mass times acceleration, so it's mv squared over r. Now, basically, what this means is that the centripetal force is what causes the object to go in a circle. If the centripetal force is not there, then you use Newton's first law. There's no force, so the object will continue to move in a straight line at constant velocity. So it will end up moving tangent to the circle, okay, at constant velocity. So to have it go in a circle, you need a centripetal force. Centripetal force cannot just be created out of nowhere. It has to already exist, since that's what causes it to go in a circle. You don't go in a circle and a centripetal force just comes out of nowhere. No, centripetal force already exists. It's the resultant force of all the forces already available, and that causes you to go in a circle. Okay? So we say something has to provide the centripetal force. It's the resultant force. Okay. There's another concept, angular velocity. Now, angular velocity is how fast you trace a circle. And the reason we use angles is because we're literally going in circles. So if you go 2 degrees per second, for example, that's your angular velocity. However, we don't use degrees in physics. We use radians. Why? Radians is a lot better. If you want me to do a video explaining why radians is better, let me know in the comments. Okay, so radians, to recap, 360 radians is 360 degrees is 2 pi radians. 180 degrees is pi radians. And the radian is just such that the angle is basically the angle such that the arc length is equal to the radius. Okay? That's 1 radian. So angular velocity is measured in radians per second. Okay? Now, we can find a relationship between the angular velocity and the regular velocity. Well, in 1 second, if you're traveling at omega radians per second, in 1 second you travel omega radians. Now, if 1 radian makes an arc length of r, then omega radians will make an arc length of omega r. So basically, in 1 second, the object has traveled a distance of omega r. But it's also traveling at a velocity of v. In 1 second, it will travel v meters, because if you're traveling at 5 meters per second, in 1 second you travel 5 meters. So v meters is equal to omega r meters. So that basically means these two distances are equal, and so v is equal to omega r. Okay, that's the relationship between angular velocity and regular velocity. You can substitute this back into the acceleration to find that the acceleration is omega squared r. Now, whichever information is given in the question, you use that to find the acceleration. So if you're given the angular velocity, you use this formula. You're given the regular velocity, you use this formula. Now, last but not least, we consider the time period, which is basically the time it takes to go around the circle once. And there's also frequency, which is how many times it goes around the circle in 1 second. That's 1 over time period. So now what's time? Well, we know speed is equal to distance over time. So that means time is equal to distance over speed. What's the distance around the whole circle? That's just the circumference, 2 pi r. And the speed? Well, the speed is v. So it's 2 pi r over v. But if you substitute v is equal to omega r, you get that it's also equal to 2 pi over omega. So the time period is 2 pi over omega and 2 pi r over v. But you use whichever one you have information. Okay, so now let's talk about the applications of this. So imagine you're sitting on a turntable, okay? And the turntable is rotating, so that means it's providing a centripetal force. Okay, otherwise it wouldn't rotate. So the turntable is providing a centripetal force. Now, since the seat is bolted to the turntable, the seat will experience a centripetal force, and the seat will rotate. However, if you're sitting on the seat, you're not bolted to the seat. So what happens is the seat experiences an acceleration, but you don't. And so you basically feel the seat moving into you. You feel the seat pushing you as a result. Okay, that's why when you sit on something that goes in a circle, you feel a force from behind. Now you might be thinking, well, if I'm not moving with the seat, then how do I move in a circle? Well, basically when the seat moves in a circle, eventually it pushes you and causes you to move along with it. And also you hold on to a seat when you move in a circle. If you don't, you'd fall off. So yeah, that's how you move with it. But since the seat is accelerating into you and you're not accelerating initially, it essentially feels like you're accelerating to the seat, even though you're not. It's just a perspective. Okay? If something's accelerating towards me and I'm stationary, it's basically the same thing as me accelerating towards the object. Right? From my reference. So there's some fictional force basically acting on me that causes me to go towards the seat. Even though that force doesn't exist, it's actually the seat pushing on me, but it feels like I'm pushing on the seat. I'm being pushed on the seat. And we call that the centrifugal force. As you can see, it's opposite to the centripetal force. Okay? So, now imagine you're in a car and you go around a bend. So the centripetal force will be towards the center of the circle. But now since the car is accelerating towards the center of the circle, and the seat is bolted to the car, it will also move to the center. It will also accelerate towards the center of the circle. But your body is not bolted to the seat, so it won't move towards the center of the circle. Your body will continue moving in a straight line, so you feel like you're being accelerated this way, even though you're not. You feel like there's a force here. There's no force there. It's just the seat and the car is moving, is accelerating this way. It's experiencing a force this way, but you're not. So you feel like there's a force pushing you this way. Okay, that's centrifugal force, and that's why when you're going around a curve in a car, you move the opposite direction. Now you can actually use this to create gravity. Let me tell you how. So basically, if you have a large wheel in outer space and you apply some centripetal force and cause it to rotate, it will rotate, right? Then we know that there's centrifugal force. If I put someone here, right, if the centripetal force towards the center of the circle, then the person in their reference frame experiences a centrifugal force opposite to the centripetal force. And that basically acts like artificial gravity. Now I'm being pushed onto the floor. So that's how artificial gravity works. Now last but not least, you've probably seen the famous experiment involving a bucket of water. And basically, you take the bucket and you spin it around. So if you consider the forces, well, there's a tension. And that tension comes from holding the bucket. It can either be due to a string or your hand, however you spin the bucket. Okay? Sorry. So when you spin the bucket and it goes upside down, the water doesn't fall out. Now let's use the principles we have learned. Why doesn't the water fall out? Well, there's a centripetal force. The tension provides a centripetal force which causes the bucket to go in a circle, okay? But the water is not bolted to the bucket. It's not stuck to the bucket. It's free to move, okay? So the water is free to move. So the water doesn't experience the centripetal force. Instead, what's actually happening is like the bucket is being accelerated this way, the water is not, so it feels like the water is being forced this way, even though it's not. From its reference frame, it feels like it is. Okay, so there's essentially a centrifugal force pushing the water into the bucket. Okay, and that's why the water stays in the bucket, and it actually will stay in the bucket if the centrifugal force is greater than, the gravitational acceleration. If the centripetal acceleration is greater than gravitational acceleration, the water will stay in the bucket. And one more thing, when you spin the bucket, you can actually spin at really, really, really high velocities and create very high centripetal acceleration. And as a result of that, the water, from its perspective, the water gets forced into the bucket with much more force. Right? The force is much stronger because the centripetal acceleration is much stronger. So it feels like the water is being pushed much harder, and eventually it can get pushed so hard that it can break the entire bucket. Okay, so basically the water becomes heavier during centripetal acceleration, and you become heavier when you go on roller coasters because of that extra centripetal force. Okay, so that's everything on centripetal force, centripetal motion, and centrifugal force, the fictitious force. If you did not understand anything or would like me to elaborate more on certain subjects, let me know in the comments and I might make a video on it in the future. So, thank you guys for watching Quantic Academy. Leave a like and subscribe, and I'll see you all in the future. Goodbye.